Hey everybody, it's Ripley again. We're back. So we figured out that solving for a line tangent to a function is important, right? So here's my function f of x, and we're going to have some value here at x equals a. And what we want to be able to do is we want to be able to figure out the line tangent at x equals a. And the way in which we do that is we throw out a lure to x equals b if we want to, and then we suck this back. And the question is what is the mathematical mechanism, the computational mechanism by which we can suck x equals b back towards x equals a? Because we need the ability to do that. And the answer to that's really simple. It's the limit. All right, so let's get ourselves a little vocabulary here. We're going to talk about the limit. I'm going to write this guy up. And we've talked about this before. All right, this is a mathematical construct that we need. Now let's make sure we understand what this means just in vernacular terms. The way that we say that this is the limit as x approaches a, sorry about that, you guys, approaches a of f of x. That's how it's spoken. Okay? Now, if it equals a number, the limit as x approaches a of f of x equals L, all right, then this guy right here is referred to as the limit of the function at x equals a. Now, there's a really, really simple way to describe what this really means. All right, let's take any function, all right, like that, all right, and let's call this right here x equals a. Now, if I'm looking for the limit as x approaches a of f of x, all right, this guy's name is f of x, all that I'm saying is I'm going to drape a piece of dental floss. I call this the dental floss definition of limit. I'm going to drape a piece of dental floss over x equals a. So as far as I'm concerned, x equals a doesn't exist. All right? Now, there's two ways to think about this. The real mathematical way is this. If I take a series of open intervals around a that get closer and closer and closer and closer to a, does that imply that there's some value over here, which we're going to call L, that if these guys get closer and closer to A, does this get closer and closer and closer to L? And in this case, that happens to be. But I have a far simpler way to deal with this. Look, take your fingers, all right, and point them at the screen on either side of x equals a. All right, and head towards x equals a. If your fingers head for the same spot, if they head for exactly the same spot, that spot that they head for, translated onto the y-axis, is the limit. So guess what? We've got a limit. Now, that discounting of x equals a, it's not even a discounting, it's a disregarding of x equals a, can give students fits. Okay? Now, what we're really saying is that as we get arbitrarily close to x equals a, but never getting there, that's really important. Arbitrarily close means, arbitrary closeness means that you're so close to x equals a that you can't tell the difference. All right? If I get arbitrarily close to x equals a, I should get arbitrarily close to y equals L. All right? That's all that it means. Now, watch this. Let's kick over here, and I'll show you another one. Let me change my colors real quick. Now, what if I do this? What if I have a function that does this? All right? And this is going to be x equals 5, and this is going to be, who cares, 17, and this is going to be f of x. So if I am looking at the limit as x approaches 5 of f of x, well, what is that saying? Now, again, remember, it's clear there's a big old gaping hole at x equals 5. Now, because it's just one hole and not an interval, we can assume that it's just a point that's missing from the function, which means when I drape my dental floss across x equals 5 and I put my fingers on either side of x equals 5 along the function, do they head for the same value? Yes. And what is that value? It's 17. Guess what? My limit is 17. And I'm done. Now, why is this important? Watch. Let's say that I take the limit as x approaches 2 of x squared minus 4 over x minus 2. Now, for those of you that have a little bit of experience with, excuse me, I'm going to take a little sip. A little bit of experience with limits, you may say, okay, well, I'm just going to plug in x equals 2, because that seems to be what happens. The problem is, if I plug in x equals 2, I get 0 over 0, which is an indeterminate form. It doesn't exist. It's not a number which exists. However, if I do just a little bit of algebra, if I take the limit as x approaches 2 of x plus 2 times x minus 2 over x minus 2. Now, look at this. Clearly, these two terms are exactly the same. Now, in algebra, your algebra teachers probably said, okay, well, let's just cancel these, and then we're going to claim, incorrectly, that x squared minus 4 over x minus 2 is actually equal to x plus 2. But we know from our Algebra 2 experience that this algebraic cancellation produces a whole. So I take the limit as x approaches 2 of x plus 2, which is, ta-da, 4. Now, what does that imply graphically? Okay, now, it's time for me to really start jumping on my high horse here. You've heard me say it in class. You're going to hear me say it these video lectures as well. You have to think about calculus in three ways. You have to think about it graphically. You have to be able to visualize graphs. You have to think about it algebraically. Hey, we did a little algebra right here. And you have to think about it numerically. Now, numerically, how would I think of this numerically? Well, we could throw this in our grapher and look at a table and see what happens, which we'll actually do in class as well. All right, so what does this thing look like? Well, it looks like that, only at x equals 1, 2, we got ourselves a hole. There's a hole in our graph. And if we were to graph it on our graphing calculator, we wouldn't be able to see this hole because the pixelation of the screen wouldn't allow us to see it. However, if we did trace it, let's actually do that. We'll come back to that later. All right? So guess what? If I take the limit as x approaches 2 of x squared minus 4 over x minus 2, it is exactly the same as the limit as x approaches 2 of x plus 2. Now, I'm not claiming that this term and this term are the same because their functions aren't the same, right? Those two functions are not the same. This function has no holes. This function has a gaping hole at x equals 2, okay? So, again, I just grab my little fingers and I drag, whoop, and I drag. Oh, but Ripley, there's a hole there. What do I do with that? Who cares? My dental floss is over it. I don't even care about it. And I know that it heads for the value of 4. All right? So that's all that there is to it. If I can look at a graph, if I can see a graph, and I'm asked to take a limit, then all that I have to do is do my dental floss finger test. All right, now the question is, what if I can't look at a graph? All right, what if I've got something like the limit as x approaches 0 of sine x over x? All right, now let's say that just for giggles that I don't know what this graph looks like. I have no idea what this graph looks like. I don't know that it looks kind of like this, and now if I was sitting here, well, that's kind of nice because check it out, this is really badly drawn. I could do my finger test at x equals 0, right? I could drape my dental floss over x equals 0, and it appears that my fingers head to the same value. All right, now that value happens to be 1. The actual limit of this is 1. But let's say that I can't do that. I don't have the ability to do that. Okay, I don't know, maybe my skills with graphs aren't top shelf yet. Trust me, they will be. Excuse me. I'm parched today.